Relaxed Knapsack QAOA approach for battery revenue optimization. Battery revenue optimization problem. Let's start with the problem formulation. We have two sources of energy which can supply a battery: a wind turbine and a solar cell. We will call them markets M1 and M2. The battery can be charged either from the wind turbine or from the solar cell, and every day it is connected to one of these sources of energy. On Monday last week, we connected two identical batteries to both markets and measured how much power we get from each source of energy every day during the week. So, we know a daily return for 7 days, the revenue. In reality, this can be the average data over the summer season, for example. At the same time, the energy stored in the battery will be sometimes released to the grid for the customers. This means that the battery will experience several charge-discharge cycles over the day. We know these numbers for the same period of time as well. This is the cost. However, the amount of energy which a battery can store will permanently decrease. The same thing happens with your smartphone. And we know the lifetime of this particular battery which we use. Namely, we know how many charge-discharge cycles it can survive. This is the maximal number of charge-discharge cycles, Cmax. Assuming that all the data remains the same, our goal is to find an optimized schedule for the next week. At which day, which energy source should we use to maximize the power collected in the battery. However, the number of charge-discharge cycles should be below or equal to Cmax. In other words, we need to maximize the return within the battery lifetime. Now we can formulate the combinatorial optimization problem. It is convenient to introduce a decision variable z. Z equal to 0 means that we are using a wind turbine, and z equal to 1 corresponds to the solar cell. Z array shows the schedule, which source of energy is charging the battery on which day. And this is the Z array for the schedule shown on the screen. One can define two functions, return and cost. These functions allow calculating the total return and the total cost over a given period of time for any schedule. Also, there is a condition that the total cost should be equal to or below Cmax. And the goal is to find an array of Z which will maximize the total return under this condition. This combinatorial optimization problem is equivalent to the Knapsack problem. The exact optimization of the Knapsack problem is NP-hard.